In this lesson, we're going to be finding gradients of functions and directional derivatives. Here we're going to look at directional derivatives in the plane. If we have a function f of x and y, and it is differentiable, then the rate at which f changes with respect to t along the curve x equals g of t and y equals h of t. Let's just move these up a bit. Then the rate at which f changes with respect to t along the differentiable curve is the derivative of f with respect to t, which is the partial derivative of f with respect to x, chained out with the derivative of x with respect to t, plus the partial derivative of f with respect to y times the derivative of y with respect to t. And let's move this up. At any point p naught of x naught and y naught, where this is a specific point such that it is that p naught, in fact, it is of g of t naught, because we know that x is a function of t, and h of t naught, because we know that y is a function of t. Let's move that up. So let's draw a graph here. I'm going to move up squeeze these up a little higher so that I have some room for my graph. Maybe we'll move this up here and then move this up here. Okay, so let's go back to black and let's draw first our y-axis. I'm going to keep that straight, and our x-axis. And we'll do this here, y, and this is x. And here's our origin. So, and what I'm going to do is let's draw this line here. And this line represents our function f of x. And let's draw on top of this our point p naught. So here's p naught. And I'm going to make my font a little smaller. I'm going to sort of dash lines down. So this is our x naught, because this is the point p naught, and this would be y naught. And now I'm going to make my font thicker. And let's draw the unit vector from point P right here. So imagine this is our unit vector u. And u, I'm going to go small again. The unit vector u in the direction of f is u sub 1 in the I direction plus u sub 2 in the j direction. I'm going to go back to blue, and we're going to talk about the blue line here, which is f, and this is represented by x, which is equal to x naught plus constant s times the unit vector u sub 1. Let's put that up there. and by y, which is equal to y naught, plus the constant s times unit vector sub 2. I'll move that up there. So that represents our line f of x and y. So this equation for df dt gives the rate of change of f with respect to increasing t, and therefore depends on the direction of motion along the curve. If the curve is a straight line and t is the arc length parameter along the line measured from p naught in the direction of a given unit vector u, then the derivative of f with respect to t is the rate of change of f with respect to the distance in its domain in the direction of the unit vector u. By varying u, we find the rates at which f changes with respect to the distance as we move through p naught in different directions. Here, our constant s represents the measures of arc length from p naught in the direction of u. We find the rate of change of f at p naught in the direction of u by calculating the derivative of f with respect to s at p naught. So the derivative of f with respect to s at p naught is equal to, we move this over, the limit as s goes to 0 of the ratio f of x naught plus s u sub 1, comma, y plus s u sub 2 minus, okay, I'm running out of room. Let me move this up. And let's extend this. You should notice this is the difference quotient. F of x naught, y naught, all over s. The directional derivative, which we have just defined here in this equation, is denoted by d sub u of f with a p naught. This is the derivative of f at p naught in the direction of u. Let's try an example of this. Let's find the derivative of f of x and y, which is equal to, f is equal to x squared plus x times y. So this is the equation for our curve. Let's move that up. And let's do that at p naught, which is the point 1, 2, in the direction, let's move this up, in the direction of unit vector u, which is equal to 1 over radical 2 in the I direction, plus 1 over radical 2 in the j direction. And I'll move this one up here to the right and see if we can squeeze all of these in together. I'll put a comma between each one so you can tell them apart. This is where our function ends, there's our point, and there's u. So let's use our definition of the derivative here. The derivative of f with respect to s, and this is our directional derivative at p naught, is equal to the limit as s goes to 0 of f of x naught plus s times unit vector sub 1 and y plus s times unit vector sub 2 minus f of x naught y naught all over s. That's our definition. Let's pull this up. Now I'm going to change my font. I think it's a little too large for what I'm doing. And so this is actually equal to the limit as s goes to 0. And we keep writing this until we've resolved the limit of f of 1 plus s times 1 over radical 2, and then 2 plus s times 1 over radical 2 minus f of 1, 2. And this is all over s. Let's move that up. Better with a smaller font. So this is equal to the limit as s goes to 0, and now we're going to put these values into the original function. We have 1 plus s over radical 2 squared plus 1 plus s over radical 2 times 2 plus s over radical 2. Let's put this together here. Minus 1 squared plus 1 times 2. And this is all over s. I'll move this one up. And what do we get? We get the limit as s goes to 0 of 1 plus, we're squaring this binomial, 2s over radical 2 plus s squared over 2, I squared the square root of 2, plus 2 plus 3s over radical 2 plus s squared over 2 minus 3, and this is all over s. Let's move this up. Oh dear, let's move this up. And I've adjusted everything up a little bit to give ourselves more room. So this is equal to the limit as s goes to 0 of 5s over radical 2 plus s squared, that's the numerator, again all over s, which is equal to the limit as s goes to 0 of 5 over radical 2 plus s. Now s is going to 0. Now we can resolve the limit, and our answer is 5 over radical 2. So this means that this 5 over radical 2 is the rate of change of f of x and y, which is x squared plus xy, at p naught 0.12 in the direction of u. So now let's take a closer look at our functions x and y, where x is equal to x naught plus s times u sub 1, and y is equal to y naught plus s times the unit vector u sub 2. Let's move these up. And these are going through the point P naught, which is x naught, the order pair x naught, y naught. So the arc length parameter s increases in the direction of the unit vector u, which is u sub 1 in the I direction plus u sub 2 in the j direction. Then we can calculate the derivative of f with respect to s. And that is in the u direction at p naught. And it's equal to the partial derivative of f with respect to x at p naught, chained out using the chain rule, dx ds, plus the partial derivative of f with respect to y, and this is at p naught, chained out times the derivative of y with respect to s. Let's move that up. And what we get is the partial derivative of f with respect to x at p naught times the unit vector u sub 1 plus the partial derivative of f with respect to x, y, at p naught times the unit vector u sub 2. I'll move that one up. And so this is equal to the partial derivative of f with respect to x at p naught in the I direction plus the partial derivative of f with respect to y at p naught in the j direction, dot product with the unit vector u sub 1 in the I direction plus the unit vector u sub 2 in the j direction. So here we're using the dot product. And what we have is that this first piece here, that is the gradient of f at p naught. And I'm going to change colors. We'll do this one in green. And this is the direction of the unit vector u. So this brings us to the equation for the gradient of f. The gradient vector, let's write that out. When we talk about the gradient vector, we use the symbol, sort of an upside down triangle, the gradient of f. And the gradient of f is a vector, and it's equal to the partial derivative of the function with respect to first parameter I, x in the I direction, plus the partial derivative of our function with respect to the parameter y in the j direction. And we'll move that up. Now this is pronounced grad or grade f, as well as gradient of f, and the symbol itself is read del, D-E-L. The directional derivative is the dot product, and it is f, the derivative of f with respect to s, and this is in the u direction at p naught, is equal to the dot product of the gradient of f at p naught dotted with the unit vector u. This is the dot product of the gradient vector at P naught and U. This gives us the directional derivative. Let's try an example of finding the derivative of a function f at a certain point P naught in a given unit vector direction. In this example, we're going to find the derivative of the function f of xy at P naught in the direction A. We're going to start by finding the gradient of the function. So the gradient of f is equal to the partial derivative of f with respect to x in the I direction plus the partial derivative of f with respect to y in the j direction. So let's move this up. So the partial derivative of f with respect to x is 2y. And that is in the I direction. Plus the partial derivative with respect to y is 2x minus 4y. So now we have the gradient. And of course, let's put parentheses around this because this is the j component. Now we're going to evaluate the gradient at P naught. And that's going to be 2 times y, which is 5, in the I direction, plus 2 times x, which is 5, minus 4 times y, which is 5, and that's in the j direction. And that's going to equal 10I minus 10j. All right, let's move that up. Now we're going to find the unit vector u, which is a over the magnitude of a. The magnitude of a is the square root of 5 squared plus 3 squared and a, which we have up here, is 5I minus 3j. So the denominator is the square root of 34, so it's 5I minus 3j over the square root of 34. So let's move this up. Now we find the dot product is the partial derivative of f with respect to x times the unit vector in the x direction plus the partial derivative of f with respect to y times the unit vector in the y direction. And what we get is the 10 times 5 over the square root of 34 plus a negative 10 times a negative 3 over the square root of 34. So let's write that down, we've got the I component from the partial derivative of f with respect to x, which is 10, times the I component from the unit vector, which is 5, over the square root of 34, plus a negative 10, which is the j component from the gradient, times the j component from the unit vector, which is a negative 3 over the square root of 34. And this is equal to 50 minus, or plus, negative times negative is a positive, 50 plus 30 over the square root of 34. We'll sort of bring this around up here, which is equal to 80 over the square root of 34. And we can rationalize our denominator by multiplying the numerator and denominator by the square root of 34. And we get 80 times the square root of 34 over 34, which reduces to 40 times the square root of 34 over 17. So the derivative of the function at p naught in the direction of a is 40 radical 34 over 17. Let's try another example of finding the gradient of a function at a specific point. Find the gradient of the function f of xy equals 5y minus x at the point 6, 3. Then sketch the gradient and the level curve that passes through that point. So the gradient of f has two components. It is the partial derivative of f with respect to x in the I direction plus the partial derivative of f with respect to y in the j direction. Let's move that up. So what we need to do is we need to find the partial derivative of f with respect to x. And in this case, when we look at this 5y minus x, well, the derivative with respect to x is a negative 1. So this is negative 1. Let's move this up. This is in two parts here. And then the partial derivative of f with respect to y is equal to 5. We'll move that up. So the gradient of f is equal to a negative 1 times I, which is a negative I, plus 5 times j, which is 5j. Let's move that up. The level curve is a set of points in the plane where the function has a constant value. To find the level curve, we substitute the point 6, 3 into the function. So let's do that. F of 6, 3 is equal to 5 times y, which is 3, minus x, which is 6. That's 15 minus 6, which is 9. This is our constant c. Let's move that up here. Maybe we'll put that down here so it doesn't take up too much room there. To sketch the level curve, we need to take our original function f of x, which is 5y, minus x and set it equal to the constant function value 9. Now let's solve for y, and we get 5y is equal to 9 plus x, and then divide by 5 and we get y is equal to 9 plus x divided by 5. Now to sketch this, there's our y-axis and our x-axis, and the y-intercept is 9/5, so just a little under 2, and the slope is up 1 over 5, so up 1 over 5. 1, 2, 3, 4, 5. So it's going to look something, this is freehand, but something like this, where it has a slope of 1/5 and a y-intercept of 9/5. The I component, which is -1, and the j component with 5, which is 5, tell us the direction that the gradient is pointing. So if we come down to here and say we're at this point, we're going to be pointing in this direction, and the gradient is going in this direction because it's going, let's find a different color, we'll go with green, because it's actually going 1 unit to the left and 5 units up. So we've found the gradient right here, and we found the equation for the level curve, and we found the direction of the gradient. Let's try another example. In this example, we're going to find the gradient of the function with respect to x, y, and z at the points -2, -1, 2. The gradient of f is going to equal the partial derivative of f with respect to x in the I direction plus the partial derivative of f with respect to y in the j direction, plus the partial derivative of f with respect to z in the k direction. So let's find the partial derivative of f with respect to x. And we get 2x times a -1/2 times x squared plus y squared plus z squared, all raised to the 1/2 minus 1, which is a -3/2. Oh, in case you cannot see that, that's a 1/2 up there as an exponent, plus the derivative of the natural log of xyz, which is 1 over xyz times the derivative with respect to x of xyz, which is yz. So let's move that up. This is our partial derivative with respect to x. And I think I'm going to come over here and let me pull this down a little bit. It was a little hard to see the exponent that we had here. That's a 1/2. Okay, so we can cancel out here. We've got a 2 here, and this 2 cancels out. And the z cancels out, and the y cancels out. And we get that this is equal to a negative x over x squared plus y squared plus z squared to the 3/2 plus 1 over x. So this is the partial derivative of f with respect to x. If we use the same procedure, we'll find that the partial derivative of f with respect to y is a negative y over x squared plus y squared plus z squared to the 3/2 plus 1 over y, and the partial derivative of f with respect to z is a negative z over x squared plus y squared plus z squared plus 1 over z. Now, if we input the point -2, -1, -2, we get, actually, let's make this x coordinate a +2, just to change it up a little bit. Okay, so if we input the points -2, -1, +2, for the partial derivative of f with respect to x, we will get a -23 over 54. Let's move that up here. And then for the partial derivative of f with respect to y, we will get a -26 over 27. And let's move that up. And for the partial derivative of f with respect to z, when we plug in the triplet point, we get 23 over 54. Let's move that up. So the gradient of f is a -23 over 54 in the I direction minus 26 over 27 in the j direction plus 23 over 54 in the k direction. And let's put a box around our final answer. Here's another example. In this example, we're going to sketch the curve of the function together with the gradient and the tangent line at a given point. Then we're going to write the equation for the tangent line. Here's the function, x squared plus y squared equals 6, which is a circle, and here's the point. The gradient vector is normal to the level curve at the point, and the tangent line is tangent to the level curve and normal to the gradient vector. Let's start by finding the gradient. The gradient is the partial derivative of f with respect to x in the I direction plus the partial derivative of f with respect to y in the j direction. So let's move this up. So this is equal to, so we need to find the partial derivative of f with respect to x, and that's going to be 2x, and it's 2x in the I direction, plus the partial derivative of f with respect to y, which is 2y, and that's in the j direction. Now, if we put in the point 1, square root of 5, in for x and y, we get 2 times 1 is 2, so 2 in the I direction, plus 2 times y, which is 2 times the square root of 5, so 2 radical 5 in the j direction. So this is the gradient vector. Now let's graph the circle that we have here, our curve. So here's the y-axis and our x-axis and our circle. And the circle has a radius which is equal to the square root of 6. And here's our point when x is 1, y is radical 5. And the tangent vector is tangent to the circle and goes through the point 1 radical 5. And the normal vector is perpendicular to the tangent vector at the point 1 radical 5. The line tangent to the curve passes through the point 1 radical 5. The equation of the tangent line is the following. The partial derivative with respect to x at the point x naught y naught, which is 1 radical 5, times x minus x naught, and x naught is 1, plus the partial derivative of f with respect to y at the point x naught y naught, which is 1 radical 5, times y minus y naught, and y naught is radical 5, equals 0. So let's put this in. The partial derivative of f with respect to x at x naught y naught is our 2. So put 2 in. And that is times x minus x naught, which is x naught is 1, plus the partial derivative of f with respect to y at 1 radical 5 is 2 radical 5. And that's times y minus y naught, which is radical 5, is equal to 0. Now let's simplify this equation. We'll distribute the 2, and we get 2x minus 2, plus, and we'll distribute the 2 radical 5, and get 2 radical 5 times y, minus 2 radical 5 times radical 5, which is 10, equals 0. Now let's combine the negative 2 and the negative 10, and we get 2x plus 2 radical 5y minus 12 equals 0. And this simplifies to 2x plus 2 radical 5y, and add the 12 to both sides, so this equals 12. So here we have the equation for our tangent line. It is 2x plus 2 radical 5y equals 12.